So this video will go over section 8.7, which is on dilution. So dilution is the addition of solvent to decrease the concentration of solute. The solution volume changes, but the amount of solute is constant. So let's look at the illustration here. To the right, in the initial solution, we have, let's say we have 10 moles, right? 10 particles, let's say that there are 10 moles. And let's say that the volume is 1 liter. So if we calculate the molarity, it's 10 moles over 1 liter, and that's 10 molar. Now, let's say we are adding just more solvent into that beaker, and let's say we double the amount of solvent and increase the volume of the solution to 2 liters. And we didn't add any solute, so we still have 10 particles. If you look and count the spheres here, you have 10 moles of solute, but this time now the volume is 2 liters. So if we calculate the molarity, we have 10 moles of solute over 2 liters of solution, and the molarity is 5 molar. So that's what dilution does. It's decreasing the concentration or diluting it by changing the amount of solvent. The number of molecules of solute is staying the same. Let's verify that by calculating the number of moles of solute. In the initial solution, to calculate the amount of moles of solute, you do molarity times volume to get the number of moles of solute. So if you do the molarity, which is 10 moles per liter, right? Because capital M represents moles per liter. So molarity times the volume, which is 1 liter. The liters cancel, and this is equal to 10 moles. So we have 10 moles of solute in beaker 1. And in beaker 2, you take the molarity, so 5 moles per liter, multiplied by the volume, and it's 2 liters here. And 2 times 5, the liters cancel, and it's 10 moles again. So we see that we have the same amount of solute in both beakers, even though we added more solvent. So the concentration decreased, but the amount of solute stays the same. And so according to the second operations we did here, we multiplied the concentration by the volume. In our case, it was molarity times volume, but it's, you know, if you take a more general form of concentration and call it C1 times V1, the volume of the initial solution, we found that it's equal to C2, the second concentration, multiplied by the second volume of the diluted solution. So when you multiply concentration by volume, it's equal to a number of moles of solute. And so C2V2 is equal to the number of moles of solute in the diluted solution, and it's equal to the number of solute in the initial solution. So this equation, C1V1 equals C2V2, is called the dilution equation or formula. And so it's very useful. And it's in your reference packet if you forget it. So let's calculate the molarity of a diluted solution. So whenever you will need to use the dilution formula, it's whenever you see that you're diluting a solution or increasing the volume by adding solvent. When you see those terms, it should ring a bell that it's about dilution. So what is the molarity of a solution when 75.0 milliliters of a 4.00 molar KCl solution is diluted to a volume of 500 milliliters? So as always, extract the information from the text, and here what is given are, so when you have a problem like that where you see diluted, you know, solution is diluted to a volume, it's the keyword that tells you it's dilution here. So that means you will need to find C1V1 and C2V2, right? and it's important to give the proper value to the proper variable. And so when you read this, it says 75 milliliters of a 4 molar KCl solution. So these two values, they go together, and it's what you started with, because then you diluted it to a larger volume. So 75 milliliters will be your volume 1, and C1 will be the 4.00 molar. It's the state of your initial solution. And so when it's diluted to a volume of 500 milliliters, so 500 milliliters will be your second volume, your diluted volume. And what is the molarity? The question is asking, and that means you're looking for the concentration of the diluted solution, so C2. So once you have given the proper values to the proper variables, then you take out the formula, the dilution formula, C1.V1 equals C2.V2. So we are looking for C2. So you want to solve for C2 and isolate C2. So to have C2 by itself, you want to divide both sides of the equation by V2, so that V2 will cancel on the right side, and then you will have C1V1 over V2 equals C2, right? So this shows how we divide both sides by V2. V2's cancel on the right of the equal sign, and then we have C2 equals C1 times V1 divided by V2. So next step is to substitute the values and solve. And here we are ready to substitute because both volumes have the same unit. If they have the same unit, those units will cancel and we will be left with a concentration unit. And so C2 will have the same concentration as C1. So if you plug in the values, you have 4.00 molar, that's C1, multiplied by 75 milliliters, that's V1, divided by 500 milliliters, and that's V2. We see that the volume units of milliliters cancel, but the molarity doesn't cancel. So the unit of the diluted concentration will be also in molarity. So in the calculator, you do 4 times 75 divided by 500, and it's 0.6. 0.6 is only one sig fig, but you need to give more than that because all given numbers here have 3 sig figs. So we need to keep 3 sig figs, and that means after the 6, we will need to bring down 2 zeros to increase the number of sig figs to 3. So the final answer is C2 equals 0.600 molar, and that's the concentration of the diluted solution. And you want to confirm that the concentration of the diluted solution is smaller than the concentration of the stock solution, which is the concentrated solution, the starting solution, which was 4 molar. So it makes sense. So let's do a practice problem now. So to what volume should you dilute 0.200 liters of 15.0 molar NaOH to make 3.00 molar NaOH? So again, there is the key word here that says dilute. So you're doing a dilution, and you have 2 concentrations and 1 volume. So you need to give the proper values to the proper variable. And so here, if you read this again, to what volume should you dilute 0.200 liters of 15 molar NaOH? So you want to dilute that 0.200 milliliters to of 15 molar NaOH. So That's going to be your initial solution here. So that means C1, the concentration of the initial solution is 15.0 molar, and V1, the volume of the initial solution, is 0.200 liters. And we want to dilute that to make a 3 molar NaOH solution. So you see that the concentration goes from 15 molar to 3 molar. So that's the concentration of the diluted solution. 3 molar is C2. And we are looking for V2, the volume to which we should dilute that initial solution. So we will need the dilution formula that says C1 times V1 equals C2 times V2. To solve for V2, because we are looking for V2, we need to isolate V2. And for this, we will need to divide both sides by C2. So if you divide both sides by C2, C2 cancels on the right side, and you have V2 by itself. And then on the left side, you will have C1 times V1 divided by C2. So it's showing up here. C1 times V1 over C2 is equal to V2. So now we see that our two concentrations are in the same units of molarity. So their units will cancel, and it's good. And then we will be left with liters. And so the volume of the second of the diluted solution will take on the same unit as the volume of the given solution. So substitutes the values of C1 and V1 and C2. So 15.0 molar is C1 times 0.200 liters, that's V1, divided by C2, and C2 is 3.00 molar. So 2 times 15 is 30 divided by 3, and it's 2.2 times 15 divided by 3, and it's equal to 1. The calculator answer is just 1. However, you have to pay attention to significant figures. And here, if we look at all the given values, they all have 3 sig figs, right? All the zeros are significant, except for the 0 in front of 0.200 liters. But to the right, those zeros are significant. So we need to keep 3 sig figs, and that's why it's going to be 1.00 liters. You see that the molarity units cancel, and you're left with liters. So your volume 2 will be in liters, and it's going to be 1 liter. So does it make sense? So since the solution is diluted by a factor of 5, because when you go from 15 molar to 3 molar, you've divided by 5 times the concentration. So then the volume should increase by a factor of 5, because they are inversely proportional. So, and if you will look at 0.200 liters, if you multiply by 5, you do get 1 liter. So the solution is making sense and is correct. Let's do a second practice. How would you prepare 400 milliliters of a 4.0% solution from a 12% solution? So if we extract the information from the text, so we have 400 milliliters of a 4.0% solution. So these two do go together. This volume goes with that concentration. And it says, how would you prepare that? So that's the end product. That's what you want to get at the end when you have done your dilution. So then that's going to be with the subscript 2. So 400 milliliters is V2, and 4% is C2, right? That's the concentrations of the end product, what you want to have at the end. So the diluted solution. And you're doing that from a 12% solution. So that tells you you're starting from the 12% solution. So that corresponds to C1, the concentration of the initial solution. And then how would you prepare that? Then the missing variable is V1. We are looking for the volume we need of the initial solution to know how much we should get, and then dilute to 400 milliliters. So if we take out the dilution formula, C1.V1 equals C2.V2, we are looking for V1. So to isolate V1 and have V1 by itself, you will want to divide both sides of the equation by C1. If you do that, V1 is by itself on the left, and then it's equal to C2 times V2 divided by C1. So let's substitute the values. We see that our two concentrations have the same units of percent, so they will cancel out. And so V1 is equal to C2, 4%, times V2, that's 400 milliliters, divided by C1, 12%. So we see that the percentages cancel, and we're left with milliliters. So the volume we will find will be in milliliters. So in your calculator, you do 4.0 times 400 divided by 12, and that's 133.333, etc. milliliters. So that's your calculator answer. We need to pay attention to significant figures as always. And here the 4.0% has two sig figs. The volume to 400 milliliters, because of the dot here, the decimal point being shown, it's 3 sig figs, right? The zeros are significant. So that's 3 sig figs, and the 12, it's again 2 sig figs. So the least number of sig figs is 2, so we need to keep 2 sig figs. So we keep the 100, the 3 for 30, and then we stop there, 1 and 3, and what comes after the 3 is a 3, so you run down, which means the 3 stays a 3, and then you drop everything after that, except that 133 cannot become 13. So you have to put down a 0 after the 3 to show that the 1 is in the hundreds place, and the 3 is in the tens place, and then the 0 is in the ones place. So you want to show that it's 130 milliliters. And so how would you prepare 400 milliliters of a 4% solution from a 12%? You would take 130 milliliters of the 12% solution and then dilute it until the volume is 400 milliliters. And that will decrease the concentration to 4%.